I can start. Okay. Welcome everybody. Today is the third day of Meet Electronic Science event. We have successfully completed our first 2 days. On first day, we have inaugurated our website in presence of senior professors, academicians of electronic science. We had a nice gathering of our alumni. Then Dr. Arnab Dotto from IIT Roorkee presented his talk. On second day, we focused on industrial exposure. We had Obhijan Bhattacharjee from TCS R&D team and Dr. Ratan Saha from Synopsys R&D team with us. Today, our focus on overseas alumni of electronic science. We had a problem today because of two opposite time zones. So we changed our time to accommodate our speakers who will deliver their speech today from their. I hope the exposure should enrich us and overall help our students have some realistic information. Now, I'll request Joy to take over the program and to continue. Off আছে দুর্জয় স্পিকার দুর্জয় মাইক্রোফোন অফ আছে
Okay, good evening to one and all, and good evening for the guys who are in India right now. And Saurabh, it is good morning, na, for you.
Yeah, it's morning. Yeah, thank you.
Well, so this is the third day of our electronic science program, and today we have with us for this session Dr. Saurabh Kumar Mukhopadhyay. Dr. Saurabh Kumar Mukhopadhyay is presently employed at Ryerson University, Toronto, Canada, as a postdoctoral fellow since May 2018. Before joining the Ryerson University, Saurabh Kumar Mukhopadhyay has worked as a postdoctoral fellow in Concordia University, Montreal, Quebec, for 2.5 years. He is a recipient of Regroupement Strategic A Microsystem du Quebec, postdoctoral scholarship. I think I pronounced it right. It's a French phrase.
Exactly.
Postdoctoral scholarship in February 2017. His research interests include biomedical signal processing, image analysis, and the application of machine learning techniques for the classification of various cardiovascular as well as physiological disorders. To date, he has published 17 papers in various international journals, 13 papers in various prestigious international conferences, one book chapter, one US provisional patent. And besides this, he has also been engaged in as an active reviewer of a number of international journals, including Nature Research, IEEE, IT, Elsevier, and Springer, to name a few. Saurabh Kumar Mukhopadhyay received the BSc Honours degree in Electronics in 2005 from APC College, MSc degree in Electronics Science in 2007, and PhD from Applied Physics in Instrumentation Engineering from the University of Kolkata, India. From 2008 to 2015, he was a part-time teacher in Department of Electronics, APC College, Kolkata, India. Now, I would like to request Dr. Mukhopadhyay to enrich us with his views on electronic science and his research work, and guide the students and the participants of electronics so that they can know actually what electronic science basically is. Over to you, Saurabh.
Okay. Thank you, Durja sir, for the very nice and exaggerating introduction. I'm really overwhelmed. And first of all, good evening. Hope I'm audible to everyone, right?
Yes.
Okay. Yes, you're audible. Carry on.
Thank you. So good evening to everyone, and hope everybody is doing well amid this ongoing devastating pandemic situation. Perhaps nobody had ever imagined that we'll be seeing such a misery in our life ever. Anyway, by God's grace, we hope everything will be ebbed out soon, and the dust will be settling down sooner, and we'll be back to our normal life again. So with that good hope keeping in mind, uh, mm, the how I have thought about this presentation is that the first 5 to 10 minutes I will take to tell my stories, like how I reached here and what's the path that led behind me, and then I will go to the actual PowerPoint presentation. So, uh, to give a um, succinct recapitulation of the path that led behind me to the point where I'm standing now, I would like to start from my undergrad studies. So in 2000, in the year 2002, I finished my higher secondary examination. I passed. Then I took admission in Acharya Prafulla Chandra College to pursue my honors degree in electronic science. So I remember the very first occasion when I first went to the APC college for the very first day is that I found that I need to write, read, and everything in English. That was a big hurdle for me at that time, as because since my kindergarten studies until higher secondary, everything I read in Bengali. So I still remember that I was talking to one of our senior students of electronic science honors, Rofi sir knows the student very well. His name is Pinkada. His nickname is Pinka. Good name is Odindam Nondi, if I'm not wrong. So I was asking him, Dada, when I see this big
Abhishek
fat book
Nandi.
of Abhishek
Abhishek Nandi.
Nondi, thank you. Yes, Abhishek Nondi. Thank you for the correction. So, asking Dada, whenever I see this big fat book of Millman Helkias, I just get lost. Like I really have no idea how to concur, and I will go through all these 3 years reading all this in English. Should I take a dictionary whenever I start reading any book? He gave me a really motivational speech that, and the crux of the his speech was like, if I could have done this and I passed and I could secure first class in honors, I'm also coming from the same background as good as you can also concur, so it's not a problem. So that kind of speech really boosted me at that time. Anyway, so that's how I started, and Rupio was taking the first class in our electronic science honors. I was literally stretching my ears like this, sir, please, this is the first time I'm listening to any lecture in English and I don't understand anything. So these are the preliminary hurdles that I had to face, and probably lots of our friends were on the same board. So that's how it was. Anyway, days were passing really nice, very enjoying. I hardly remember how many days I spent in the classroom and how many days I spent in the canteen. So days were really nice. Then what happened? So in 2015, when I got the final result of my honors, like the final BSc degree, I found that I got 3 marks less than first class. So at that time it was 480 to secure first class. I got 477. So Rofi sir, Fidjo sir, and at that time Ranajoyda was there. So all of them suggested that why don't you submit your 2 theory papers for the review. I did that. So I just required 3 marks. Fortunately, like in one paper, when the review result I got, I found that in one paper I got increased by 3 marks, what I really required. In another paper, I got 2 marks less. So my marks was reduced. So all of it, in total, I got 1 marks increase. So from 77 to I did 78. So I couldn't secure first class in my BSc honors. Anyway, probably in the second or in the third call, in the third list, I got admitted to Science College for pursuing my MSc degree. But yeah, MSc it's quite predicted that you will get first class. And the teachers who are taking the class and those very persons are taking the questions, is no wonder that I got a first class in MSc electronics. It's not that difficult compared to our undergraduate honors studies. Anyway, then I finished masters in 2007. Then I was just sitting idle for some times. I was just submitting my CVs to different colleges for getting a part-time position. But at that time, I was not getting. So one day I got a call from APC College that they were in need of a part-time lecturer at that time. I gave the interview and got the chance. Since 2008 January, until 2017, sorry, 2015 October. I did the same thing for the whole 7 years. I was employed in APC college as a part-time lecturer. So when I first joined there, then I was taking as advice from Professor Subros and all other senior professors on the just joined at that time, and Prosenjit sir was there before even I joined. So if you have chosen this career as your profession, then why not to pursue a MTech or a PhD degree? So I thought, okay, MTech, I don't want to go into that study and like intense study and examination again. So it's better for me if I could get a position as a PhD researcher. So then I approached, so
আমি ওর এই রুটি রুটি
since electronic science was my home department, so
যা করবো তো তাই তো মানে রুটি
I approached. Hello, hello.
You're audible.
Okay, okay, okay.
You're audible. Continue.
Oh, thank you. So I at that time I approached perhaps all the professors in the Department of Electronic Science. Now I would say, fortunately, very fortunately, at that time, none of the professors, they were free to take me. Like all the seats they had at that time in PhD position, they were all full. So they told me that the best option I got from Sanatan sir, Sanatan Chakrabarty, he told me that okay, I would like to consider you as my as my PhD student, but not right now, because you have to wait for another 1.5 years, because I have to outgoing PhD candidate, but not at this moment, maybe in next 1.5 years. So I'm keeping you on hold. So in the meantime, you start studying all these things and be in touch with me. So definitely I'm consider you as my PhD student. So I was doing that in the meantime. And Dr. Subro Ghoshal gave me another option. Okay, you are doing, like you are waiting and studying in the meantime, why not to explore other options? So he gave me another contact. I went to applied physics department to Professor Dr. Madhuchanda Mitro, and I convinced him. She told me that, okay, I am giving you these tasks for homework, do this job, come back to me, show the output, then I will consider. I'm not giving you any word right now, I will see. So it was kind of errand I was doing for the 3-4 months that time, and finally 3-4 months she got convinced and told me that, okay, I'm not super happy with you, but I can take you on board. So sometimes at the end of 2009 and beginning of 2010, I don't remember exactly, at that time, I started working in Madhuchanda Mitro's lab in the field of biomedical signal processing, which was completely a new subject for me, because all my education beforehand, that everything was on electronics device, semiconductor and all those stuffs. But in the meantime, what I did, actually, I learned programming languages with my own interest, which was never there. Good to see Sucharita madam here. So at that time, so I approached, I started working with Dr. Madhuchanda Mitro, and Dr. Sucharita Mitro was there as my co-supervisor. So I was doing. Then finally, in 2014, sometimes the mid 2014, I submitted my thesis. The foreign reviewer took more or less like 3 months to send the review report. I don't know where it went. But the Indian reviewer, thesis reviewer, he or she took like 8 months for reviewing the thesis. Anyway, in the meantime, I started applying for postdocs left and right. No matter what I'm applying, no matter what the country, what the university is, in India and abroad. Fortunately or unfortunately, I didn't get any response, not even a reject response from any Indian professor in West Bengal, around India, everywhere. But I was getting some responses from outside, but they wanted to have me the final PhD certificate in hand. But at that time, I never had that because my thesis was pending. So, but still, I kept applying. So the offer I got at that time, I lost as because I didn't have that certificate in hand. But finally, when I got the certificate, I got another option here in Montreal and Quebec, Concordia University. So the fellowship was for only 1 year. So I came, leaving behind everything else in India and college. But that was really a kind of heartbreaking for me. Like I was attached to APC college for as a student for 3 years, as a part-time lecturer for like more than 7 years. So 10 years of engagement I broke just in one day. So that was really a big heartbreaking event for me. Anyway, so I came here, started working. Then over time, my fellowship got extended. So I spent like exactly 2.5 years in Concordia University. And the day I finished there in Concordia University, exactly on the very next day, I got another postdoctoral fellowship here at Ryerson University. So overnight I had to I had to pack and wrap up everything and come over by bus here, which is like at least 800 kilometers apart. So then I started, and since 2018 May, I started as a postdoctoral fellow here. So I'm continuing with the same. So this is the what and I have done before since my undergrad to PhD and my first postdoc. So yeah, perhaps I'm not taking much time in elaborating on this. Okay, so now let's go to the actual slide presentation. Okay, let me share my screen. Enter screen. Okay, yes, my slides is on the screen, right?
Yeah, it is
Yeah.
visible.
Okay, so the headline of this presentation is like recent advancement in the field of biomedical signal processing research. So I will try to elaborate like how I have adorned my presentation. The slide presentation is that I'll give the research areas which researchers are doing around the world in recent days, how they used to do in previous days, and what are the recent advancements in this field, and how the research is going in current times. That's how I will try to keep the presentation as laymanish as possible, so that everybody, I know people from different background are here, so I'll try to make it as laymanish as possible. So let's get started. So first, the first question what comes in our mind is that what and why biomedical signal processing? So biomedical signal processing is playing around with the different types of biomedical signals. So what are the biomedical signals? There are tons, and these are the most common: ECG, electrocardiogram, photoplethysmogram. This is a kind of new signal, but we are aware in other way around. Sometimes who are using smartphones, perhaps you might have seen there are lots of apps which ask you to put your left finger, the first finger of your left hand, to cover your camera and the flashlight, and then they calculate your heart rate and show the screen that how your heart rate is. That's the signal which is called PPG, and that's how it looks like. Then EMG, electromyogram signal, which is basically collected from the skin, and electroencephalogram, EEG. So these are the very common biomedical signals used by the researchers. They are the hot signals, you can say, people will like to process. What biomedical signal processing is? So whatever I do, whatever we the researchers do, the processing on biomedical signals, it goes not limited to, but in any of these topics. Like each and every tract, each and every module of these steps itself a big area of research. So these are like acquisition, collecting the signal from human subject, denoising, expelling out the noise, compression, steganography, feature extraction, and classification. These are the stratification of biomedical signal processing research areas. I will try to touch upon as gentle as possible on each of these topics. Let's see. So why biomedical signal? Why would they do that? What's the necessity? In one word, to make the life easier, healthier, and even more faster, and also to get to stay tuned what is actually happening inside our body, which we really can't see through our naked eyes. So these stratification, these modules goes well with each and every biomedical signals, be it ECG, PPG, EMG, EEG, EOG, whatever. So these are the building blocks of biomedical signal processing research. So since the signals I am working on or have been working is the ECG signal. So I will try to explore how ECG signal goes well or fits with each of these modules. So let's start with acquisition of an ECG signal. So this is the basic, very simple, very basic block diagram to acquire an ECG signal. So L1, L2, L3, these are the electrodes, which in ECG jargon, these are called the leads. So these leads are basically attached to the hands and legs and also sometimes on the chest. And from there, the signal is collected. It goes to the ECG circuit like sampling, quantization, all these things. And then it is transmitted to the PC or laptop, any other electronic storage devices. The basic difference between ECG acquisition systems and any other signal acquisition system, be it voice, be it a cosmic signal or anything, the basic difference lies is that the flow of signal should be in one direction, from the body to the sensor, in no way the other way around. Because as far as human life is concerned, you have to take utmost precaution to make sure that the current is not flowing in the opposite direction. Because a fraction in a fraction of second, if the signal current flows on the other way around from the sensor to the human life will be in danger. So that's the main thing we always need to keep in mind. This is the type of ECG acquisition system which we use in our lab, and also lots of biomedical signal processing laboratories use these types of ECG acquisition systems. The latest development in this area is the smartwatch. So you don't need to go through all these leads and wires connected to your body. Your wristwatch is enough to acquire the ECG signal. So that's sometimes people use to acquire signals and to stay tuned how their heart is reacting, responding. The classical ECG acquisition systems, they all follow the Nyquist sampling rate, that is twice the sampling rate of the higher upper bandwidth of the ECG signal. So there's the sampling rate that is used. All the ECG acquisition system follows. Recently, in recent days, there is another thing called compressive sensing. It's a hot area of research. Perhaps you could explore this topic if you want. And I hope there is a lots of opportunity you come up with novel solutions and get published a bunch of papers. This compressive sensing theory says that a signal can be acquired even at a lower sampling rate compared to Nyquist if and only if a signal is sparse in time and frequency domain. That means sparse signal, the signals we call sparse signals are those which are where the information is not present continuously in time domain, also in frequency domain. So we have the luxury to use this technique in biomedical signals and other type of signals, like also in voice signal to some extent, because signals are not present all the times, always in time domain, and definitely in frequency domain. So this is a new area of research. So this is the basic block diagram of any compressive sensing data acquisition system. That is, here phi is a binary matrix, contains 0 and 1, and the length and breadth, like the dimension of this matrix, is fixed. X is the original incoming ECG signal or any other type of signals, and Y is the final output. So if we when you get the output at Y, we'll say the original ECG signal is present, what actually we are recording, but even at a less sampling rate compared to Nyquist. So you can explore this topic if you are interested. Then denoising of biosignals, denoising of an ECG signals. So by nature, ECG is a very low frequency and low amplitude signal. whose frequency band ranges from 0.5 to 100 hertz. Very low frequency signal. Also, the amplitude is also very low in the order of microvolt. That's why all these acquisition system specially have a amplifying unit to make it bigger. Since it's a low frequency signal, lots of different types of noises attacks ECG signal even at the time of acquisition. So what are the different types of noises? The first one is baseline wonder. It's not a big deal to expel out, to denoise this by baseline wonder. Baseline wonders means when the person is walking or even when the person is breathing, because of the expansion and the compression of the chest, that undulation is added with the ECG signal. So that is called baseline wandering, not a vulnerable noise. Power line interference noise, that is the line frequency, 50 or 60 hertz power line interference noise, that which contaminates the ECG signal. It is also easy to expel out using a notch filter or band stop filter. Electrosurgical noise, like when ECG signal is getting recorded and some other types of machines are running around that ECG acquisition system, those kind of electrical surges comes and attack the ECG signal and gets contaminated. This is also not a very difficult types of noise to expel out. The last one is motion artifact. This is such a noise, a very notorious noise to discard from the ECG signal, as because the frequency band of this motion artifact noise overlaps with the frequency band of the ECG signal. That's why it is very difficult and sometimes almost impossible to expel these noise out from the ECG signal. This is a example how ECG signal gets corrupted. So the first half and the last half of the ECG signal we see more or less clean, but the middle portion of the signal is highly contaminated with noise. So if such an ECG signal is given to the doctors, very difficult for the doctors to diagnose the disease and to trace the ECG signal. So that's where the denoising, we need to denoise the ECG signal. So the classical choice is band pass and notch types of filters. So why don't you create a band pass? Why don't you implement a band pass filter having lower and upper cutoff frequencies to expel out the out of band noises, and a notch filter for the power line interference noises. So this is the classical and very common choice for denoising ECG signals. However, in recent times, wavelet transform, empirical mode decomposition, and singular spectrum analysis, these techniques have been used by the researchers to denoise the ECG signal to a great extent compared to the band pass and notch filters. However, all these techniques, wavelet transform, empirical mode decomposition, singular validity, they have their own advantages and disadvantages. What are those? Like band pass notch filters, less complex. You can calculate all those numerator and denominators by hand and then fix it in the system. But the problem is sometimes non-linear phase response. So if the phase response is not trillions, that's gonna be vulnerable for any sort of biomedical signals, be it ECG or PPG, whatever, no matter. So this is the downside of classical band pass filters. So that's why the wavelet transform, EMD, and other techniques are used. So wavelet transform, very high performance, but on the downside, it's a function dependent. Function dependent means there are a bunch of mother wavelet function, out of which you need to choose one and you need to fit with your signals. Fortunately for ECG signal, we have such a mother wavelet function which goes good with the ECG signal. But for other biomedical signals, I'm not so sure. So that's a boundary. So that's a real problem. For empirical mode decomposition, it's less complex and data driven. What the meaning of data driven? For wavelet transform and band pass filters, they have a notion that have a fixed idea that, okay, this is the signal, this is the noise, we have to discard this part, we have to keep this part. But for empirical mode decomposition, singular value analysis, these are kind of data driven. They don't have any any notion before getting this, before seeing the signal beforehand. So it modulates its working principle, its steps based on the incoming signal. So these are the good points. However, the downside is sometimes mode mixing is a problem for empirical mode decomposition. What is mode mixing? Basically, these types of transform based techniques, they breaks the incoming signal into different frequency bands, and then they enumerate which band to keep, which band to discard. Sometimes these bands overlaps. Like we are quite known that this band will contain the signal, another band will contain the noise. So discard this part, keep this part. Sometimes it overlap. In which band we don't expect to have a signal that contains noise and vice versa. So that is called mode mixing. We need to deal with those. Another thing is singular spectrum analysis. So these are the new techniques which have been used by the researchers around the globe, and there are lots of opportunities if you want to explore. Okay, so then this is a piece of output using singular spectrum analysis based technique, where the blue one is a very noisy ECG signal and red one is the denoise signal. So it's I would say it's a good denoising technique. So, okay, so then compression. Why compression? Why is it required to compress the ECG signal? So first of all, perhaps we have seen, like when a person goes to the hospital, lots of sensors get attached to his body, and the doctors monitor the person for a long time, 24 hours, maybe 1 day, 1 week. So the thing is, just for one person, if an ECG signal is recorded only for 1 hour at the nominal sampling rate, that is 250 hertz, it takes 4 MB of memory space in computer or any storage devices. Now, imagine in a government hospital like Arjikar, thousands of people get admitted every day, and only ECG is acquired from all these patients. How much memory it gonna take to store all this signal? It's enormous. So that's where the compression techniques come into play. So what are the classical techniques that had been used in before, in long back, that Hoffman coding, Runlen encoding, these very standard compression techniques. But in recent times, researchers are also trying to explore compression in other domain. The basic mantra of compressing any signal or any type of thing is the finding the redundancy. So Hoffman coding, these types, or Runlen encoding, these techniques try to find the redundancy in time domain. Recently, researchers are trying to find the redundancy in frequency domain, also in statistical domain, and also in compress sensitive domain. The technique which I already have told in the acquisition slide. So these are the techniques. So yeah. So I'm going to tell about only one paper. Like the paper got published in recent times, that they take the ECG signal, try to find the redundancy in statistical domain, and then compress the ECG signal, and finally they the output of the compression system is basically ASCII characters. So what they do, basically they take the ECG signal, compress is left and right, and this particular algorithm gives a compression ratio of about like 65:1. That means if the size of the original ECG signal is like 65 gigabyte, it will be reduced to 1 gigabyte only, without compromising with the quality of the signal. And this is how it works. Basically, take the ECG signal and finally outputs a string of ASCII characters. So it basically a twofold benefits. The thing is, ECG signal after compression, it is converted to ASCII characters. So nobody can even imagine that this smiley signs contains an ECG signal. So it's a compression and encryption as well. Okay, then steganography. What is steganography? Steganography is basically embedding your personal information inside the signal itself. It may be ECG, maybe PPG, whatever. Sometimes, like when a patient is admitted, his data is getting recorded. At the same time, the practitioners need to keep his personal details, name, date of birth, card number, phone number, all other information in a separate folder. Instead of doing that, nowadays what researchers are doing, they say that no, you don't need to create another file. Why not to embed this all this information inside the ECG, inside the signal itself, so that first of all nobody could even try to hack the signal, like personal information and all these things, and also that will be secured, more secured. So what they do, the classical technique is the least significant bit replacement in the time domain. So they take one voltage value, convert it into binary, replace the least significant bit with the patient's information like name, date of birth, etc. But the thing is quite easy, like intruder, if they want to hack your system, anytime they could do that. But definitely this is an effective one. So what recently nowadays researchers are doing, they are doing the same thing basically, but in frequency domain. They break down the signal in different frequency band and replace the information, personal information, in different frequency band, and then don't disclose in which frequency band the information is present. This is one. And also data scrambling, like they break the signal, mix with the personal information, scramble it as if the egg scramble, and they just send it to the other side. So that's how they reduce the potential threat. So this is a really good topic to explore. This field is really not explored to date. So if any of you are interested, you can explore this topic. Then feature extraction. This is another area of research. So what basically doctors do when ECG signal is given to him? Suppose this is a normal ECG signal. So doctors know over the years of expertise how a normal ECG signal looks like. So what they do basically, they calculate the height and time difference between successive beats. They calculate all these things in their mind when they see the ECG signal, and all of a sudden, if an abnormal ECG tracing is given to him or him or her, definitely he gonna see that how it is how it deviates from an original ECG tracing, and that's how they come up with a solution or decision that it's a normal or abnormal. If it is abnormal, what type of abnormality is present? Now we have to do all these things in computer, because sometimes ECG data is recorded for a very long time. Like if the doctor sent you for a Holter monitoring, the data will be recorded for 24 hours. I personally went for a Holter recording for 24 hours. I know I had to carry that big bunch, that big record, that big box, and I had to doctor attach those electrodes in my chest 1 year back. So I know. So what are the classical features the computer that are extracted using computer? Time domain features like what is the height, what is the time difference, statistical features like kurtosis, skewness. These are the features researchers have been using automated algorithms. Now researchers are also trying to find deep information from the time domain, also in frequency domain, both in time frequency domain, from the wavelet frequency transform domain or Fourier transform domain, and also some trigonometric and geometric features like area, maybe the angle that is created between different peaks. These types of features which gives a deep insight of the ECG signal in hand. And so now the thing is, when we have extracted all those features using our programs, now what the meaning? Like we have to utilize these extracted features, and we have to come up with a output that tells you, okay, you are normal, your heart doesn't have any anomaly, any abnormality, or you have this particular disease. So that is called basically classification. machine learning techniques are the answer. Okay, what is machine learning? The very preliminary version of machine learning is the if-else structure. Like perhaps all of you know programming to some extent, so they are quite familiar with if-else structure. So you know that if this amplitude is ranges from this value to this value, it's normal. If the time difference ranges from this value to this value, normal. If it is not that, deviates a lot, then it is abnormal. So you can write your own if and else algorithm to classify the disease. But sometimes what happens if the number of variables are a lot, tens of thousands of variables, not even that, when the variables are itself an array, so you have to deal with numerous digits. It's doable. It's not that completely you cannot do that, but it will take your whole life to design such a classifier using if-else logic only. So what the researchers do, there are some well-established classification algorithms where you need to fit your features, and the classifier will tell you, okay, these are the outputs. So the classical machine learning techniques are support vector machine, linear discriminant analysis, k nearest neighbor. These are the hot choice of the researchers had been or has been. Recently, in the last 5 years, I would say, there is another technique called deep learning. It's basically ruining, like it's giving left and right in every field of research, where they are basically replacing all those primitive classical techniques, replacing all those things, and deep learning is giving good results. So, but
Gaurav,
yes, sir.
please, how long your slides are there? How long you will take?
I will take like 5 more minutes. I have 17 slides.
Okay.
Am I writing? I'm running out of time.
No, it's okay. But our next speaker is already ready, huh? And
Okay.
so, just okay, 7 minutes, 10 minutes, no problem. Okay.
Yeah, I'm almost done. Yeah.
Okay.
Okay. So, okay. So these techniques have their own advantages and disadvantages. So these are the techniques, the classical machine learning techniques. They are explainable. Like how you are getting the output, you can backtrack. You have solid explanation behind that. But for deep learning techniques, you really don't have. Sometimes, like I haven't came across any articles where the deep learning has been used with a acceptable explanation. It's kind of black box. In lots of areas of research, it has been implemented successfully, but in case of biomedical signals, doctors are really skeptical, as because the medical community perhaps not going to accept any output, any decision, any solution which doesn't have any explanation. So these are the techniques. Anyway, so what I'm doing right now, my present research focus is on emotion recognition from biomedical signals, any, be it ECG or PPG, whatever the other signal. So what we do basically, so different types of emotions like fear, anger, joy, they basically react differently in our cardiac system. So when we get all of a sudden we get so scared, our hearts started beating differently. When we are so happy, our heart beats differently. So these types of emotions are registered in the heart rate variability, how the heart is reacting to all these emotions. So this is one topic what I'm recently working on. You said that what's the meaning of doing all these things? Like why you want to recognize the emotion? Because you can fake your emotion. Why would I fake my emotion? In this part of the world, the basic problem is with the drug addicted people. Sometimes, you know, here, like doctors do not, like, you cannot buy medicine without having any prescription prescribed by a government approved doctor. Sometimes what people do here, they go to the doctor, say that, oh, I'm having a severe pain in my head or my leg, give me some medication. And when you say that I'm having a pain, probably there is no way to guess that whether you're having a real pain, you are just faking your emotion. So what doctors do, they give you some medication, they take that prescription to the medical drug store, they get that medication and get intoxicated. So just to stop that, this research is getting a focus here. in recent days. And also, I'm recently working with a medical device company where they're creating garments where the yarns of the garments are basically the sensors. So all the times signals are acquired from body, and they always keep you update what is happening inside. So that's a kind of thing. Okay, so next thing is what is the color of your ECG? That's a very interesting topic I'm working recently. That is, we are taking. There are lots of electronic devices where you can record your ECG signals all month around, all day around, all year around. So what's the meaning? What's the meaning if every time you need to go to the doctor and see, doctor, what is happening? I don't understand. So to make it more point of care, so that you can also understand what is happening inside you. So we are taking an ECG signal, we're converting these things into an image like this. It's not an image of the ECG itself, it's an image in frequency and statistical domain. Here, these bright pixels are basically representing the abnormalities, and each and every types of color has its own trait of abnormality. So if you see this color, you might have this type of abnormality. If you see another color, you will have other type of abnormality. So that's how we're doing some image processing techniques and come up with a solution. So our final intention is to, instead of watching the ECG signal in your wristwatch, at the end of the day, you will get a picture in your wristwatch, and thereby you can see what is how your cardiac status is. So that will be much more convenient for the layman who doesn't have any expertise in medical domain. Okay, so that's all for me. I'm really sorry if I have bored you anyway. Thank you.
Sort of. Hi, Sarvanu this side. I have a small question, if you
Sure,
can
sure.
help me understand.
Sure, sure.
What has been your industry, engagement of your research in terms of studying the emotional aspects and putting your machine learning and predicting the emotional, or rather our health of an individual? Has there been in an industrial acceptance of it? It has been productized somewhere? uh,
Yeah.
or if you can elaborate on that. And that's a very interesting topic, because day in and day out we run through multiple interactions with multiple peoples, and our emotion ranges from fear, from hatred, from anger, from anxiety, and very others, and how that influences our health systems. Is there any way to put it into a machine learning technique and get predictive analytics out of it? Is there any thought process on that, or any industry adoptions, if you can highlight on that?
Sure. So the same project is going on with two different industry. One is it's called Salisbury. It's basically a Hollywood project. Like they want, their main intention is to check, like when they are the people they are working on, when they comes to the stage or in the set, how they react. Like sometimes they react very badly, and just to get an real-time update, like how they're gonna perform today. So they want to enumerate all these things beforehand, taking to them to the set. That's one thing. Another thing is there is an industry called Mayant. That's a Toronto-based company. What they are doing, they are basically manufacturing garments where the yarns of the garment is fiber, optical fiber, and it's connected with thousands of tons types of sensors. So they are collecting all these bio signals all day around. So what they want to know basically, when you drive, one aspect is that when you drive, sometimes you get out of mind, or like you are thinking something else, which is not good for any when you are driving. So the main intention of that garment is that they are collecting the signal, processing at the very on node, and then will give you a pinch, maybe electrical impulse or some magnetic impulse to help you come back in the real world, so that you are driving, don't get distracted. So that's one aspect of this research work. Another thing that I have already told, like to stop drug abuse, because sometimes they go to the doctor, say that, oh, I'm having a pain, because there is no definition of pain. Like you cannot say, if I say that I'm having a pain, I'm severe headache, there is perhaps there is no way to justify that. So what they do, they take the medication from doctor, the prescription, go to the drugstore, buy it, and get intoxicated. So the government is really concerned about that, to stop that. That's why they are really interested in this kind of project. So when you have that, you just feed that machine to the person who is saying that I'm having pain. Check the heart rate variability, whether he's really having a pain or he's very normal, just trying to fake the emotion. So that's how they come out, and to stop these types of things. Like, am I?
Yeah, that's
Okay.
excellent. That's excellent, sort of.
Okay,
Yeah,
okay,
and
okay,
that's a good insight into industry adoption of your research work, and this is definitely going to be in good for mankind. Excellent work. Yeah.
Thank you. Let's see. Thank you for the appreciation.
We have some questions there in the chat box from
Okay, chat.
Yeah, there's some questions.
Could you please tell me how? Okay, this is a chat box.
এই সৌরভ,
Okay, so অয়নকান্তি প্রধান, হ্যাঁ স্যার কেমন আছেন? প্রণাম
ভালো
নেবেন
আছো?
স্যার।
নমস্কার।
হ্যাঁ স্যার আমি ভালো আছি। হ্যাঁ হ্যাঁ,
ভালো
সামনে থাকলে পায়ে হাত দিয়ে প্রণাম করতাম, কিন্তু
না না ঠিক আছে, এখন তোমার উন্নতি দেখে এবং ভালো বক্তৃতা শুনে খুব খুশি হলাম। ইন্ডিয়াতে তার কি স্কোপ আছে বলো একটু।
স্যার ইন্ডিয়াতে একদম পশ্চিমবঙ্গে বলতে পারছি না, তবে হ্যাঁ ব্যাঙ্গালোরের কিছু কোম্পানি আছে যারা কিন্তু কাজ করছে বায়োমেট্রিক। এই যে কথাগুলো বললাম, মানে টপিকগুলো বললাম, একদম সেই টাইপের টপিকেই ওরা কাজ করছে। তবে স্যার রিসেন্টলি শুরু হয়েছে আমাদের ইন্ডিয়াতে এই বায়োমেডিক্যাল রিসার্চ, এই ফিল্ডটা রিসেন্টলি শুরু হয়েছে, খুব পুরনো নয়, যেটা হয়তো অন্যান্য দেশে একটু অ্যাডভান্সড। তবে হ্যাঁ হচ্ছে, আমাদের দেশেও কাজ হচ্ছে নিঃসন্দেহে।
তুমি কি মন্ট্রিলেই আছো না?
না স্যার, আমি মন্ট্রিয়ালে ছিলাম 2018 মে পর্যন্ত, তারপরে এখানে টরন্টোয় আছি স্যার এখন।
টরন্টোয়?
হ্যাঁ স্যার, হ্যাঁ।
বাহ, ঠিক আছে।
আপনি কেমন আছেন স্যার?
মোটামুটি আছি, ভালো আছি।
আচ্ছা স্যার, প্রণাম নেবেন। হ্যাঁ, ভালো থাকবেন। হ্যাঁ হ্যাঁ।
Saurabh, there is some questions from Ayon and Moutushi Dotto Choudhury. Ayon Kanti Pradhan, Moutushi Dotto.
What type of capacitor used in NOS type of filter? ওটা হচ্ছে গিয়ে তোমার ওই পেপার ক্যাপাসিটার বেসিক্যালি। আমি যেহেতু দেখেছি ওটা একদম পেপার ক্যাপাসিটার ইউজ করে, কারণ
পিএইচডি করে গেছে অনেক।
পেপার ক্যাপাসিটার কেন ইউজ করে? পেপারকে প্রথম কথা ছোট স্মল সাইজের জন্য, আর ওটাকে হ্যান্ডি করতে হবে। বাল্ক সিস্টেম বানিয়ে তো লাভ নেই, কারণ এখন সবাই চাইছে ইসিজি রেকর্ড হবে যাতে কিনা ইয়েতে হয়, মানে অন রিয়েল টাইমে হয়। আর যদি একদম স্পেসিফিকেশন চাও কোন ক্যাপাসিটার ইউজ করে, আমার ল্যাবে একটা ছেলে করে ওই এই ডেটা অ্যাকুইজিশনটা, আমি তোমাকে ওই নাম্বারটা তোমাকে আমি পাঠিয়ে দিতে পারি। আমার এক্সাক্ট মনে নেই, কিন্তু আমি যেহেতু এইটা একদম অ্যাকুইজিশনটা আমি করি না, আমি পাঠিয়ে দেবো, আমাকে একটু মেল করো। ওকে, is there any established correlation between ECG and EEG on the basic emotional point of view? Definitely, হ্যাঁ অবশ্যই আছে। তার কারণ হচ্ছে যে ইসিজি, দেখো ব্রেন আর হার্ট এই দুটো একদম মানে ইনসেপারেবল, ভীষণভাবে ইনসেপারেবল। তুমি যখন কষ্ট পাচ্ছ, ঠিক তোমার ব্রেন ওয়েভ, বেসিক্যালি ইজিতে 4টে ওয়েভ হয়, আলফা, বিটা, ডেল্টা, গামা। সো যখন তুমি ধ্যান করছো, বেসিক্যালি মেডিটেট করছো, ওই 4টে ওয়েভের মধ্যে 3টে ওয়েভ একদম মানে জিরো হয়ে যায়, শুধুমাত্র একটা ওয়েভ বেঁচে থাকে, গামা ওয়েভটা। তো তুমি যখন কাঁদছো, তুমি যখন প্রচন্ড আনন্দ করছো, তখন ওই কোনো না কোনো একটা ব্যান্ডে না খুব বেশি ফ্লাকচুয়েশন হয়। তো যারা ইইজি টেকনোলজিস তারা এইটাই বেসিক্যালি চেক করে। আর ব্রেনে যখন কোনো কিছু হয় তখন সেটা অবশ্যই হার্টে রিফ্লেক্ট করে, কারণ সাইনোআর্টেরিয়াল নোডটা সেরকমভাবে জোরে পাম্প করে বা আস্তে পাম্প করে। তো এটা হার্ট রেটের ওপরে। এখন তুমি বলতে পারো তাহলে ইমোশন রেকগনিশন ইজি থেকে তো বেটার হবে, খুব বেটার হবে, কিন্তু ইজি না অনেকগুলো সেন্সার থাকে, অনেকগুলো সেন্সার থাকে। তো অতগুলো সেন্সার মেশিন লার্নিং এ ফিট করলে ডেফিনেটলি হয়তো ভালো আউটপুট পাবে, প্রচুর সময় লাগবে। আর ওইরকম একটা বগা একটা সাইজের একটা মুকুট মতো সারাক্ষণ মাটিতে বসে মানে পরে বসে থাকা, এটা খুব কাম্বারসাম। ওটা চায় না লোকজন করতে। ওর থেকে হাতে একটা ঘড়ি পরবো, ওখানে ডেটা রেকর্ড হবে, মানুষ অনেক খুশি থাকবে। হয়। অ্যাকচুয়াল কোশ্চেনটা কি ছিল? এস্টাবলিশ রিলেশন না, এটা পুরোটাই নোশনের ওপর হয়, কারণ বিজ্ঞানে বোধহয় এখনো ব্যাখ্যা নেই, আমি পার্সোনালি পাইনি। তবে এটা আছে নিশ্চয়ই, মানে আমরা আশা করি আছে।
আসলে আমি এটা কোশ্চেন করতে সৌরভ, আমি মৌটুসী। সৌরভদা, আমি মৌটুসী।
হ্যাঁ বলো।
বলছি যে মানে আমি কোশ্চেনটা এই জন্য করছি যে কারণ কি প্রচুর লোকজন, আমি কিছু কাজ কেমব্রিজেরও দেখেছি, জেইউরও দেখেছি, যে লোকজন সিগন্যাল প্রসেসিং করছে, মানে ইমেজ প্রসেসিং করছে, লটস অফ ডেটা এবং তার ইমেজ। তো স্ট্যাটিস্টিক্যালি কোনো এস্টাবলিশ ডেটা পাওয়া সম্ভব কিনা, মানে দ্যাট ইজ অ্যান ওপেন সিস্টেম।
কোথাকার কোন
না,
সিগন্যালের?
মানে ইইজি অ্যাজ ওয়েল অ্যাজ ইসিজি।
হ্যাঁ, কি বলছো? পিটিভি physionet.org, physionet.org, ওটা তো বেসিক ওয়েবসাইট, তুমি সব ধরনের ডেটা পাবে, ইসিজি, ইএজি, ইএমজি, আর তাছাড়াও আরো অনেক অনেক ডেটাবেস আছে যেগুলো থেকে ডেটা ডাউনলোড করা যায়, ফ্রিতে ডেটা ডাউনলোড করা যায়। আমাকে মেল করো, আমি তোমাকে লিঙ্কগুলো দিয়ে দেবো, কোনো অসুবিধা নেই।
I have a question, Prashanjit. Can I ask?
Yeah, obviously.
Okay, Saurabh, I'm only, my question relates to, you were talking of some people faking their, they want drugs and they are faking, basically they are faking something. Wouldn't that also involve some, some changes in the contours, facial contours and all that? So could not image processing be brought
এক্স্যাক্টলি হয়,
correlated with this?
এক্স্যাক্টলি, সেটাও একটা দুর্দান্ত রিসার্চ টপিক। সেটাকে বলা হয় হ্যাঁ, আমি বুঝতে পেরেছি আপনার প্রশ্নটা। আপনার ওটাকে বলে আইপিপিজি, ক্যামেরা পাতি একটা মোবাইল।
I was saying that can't you correlate that image processing analysis with your work as well or not?
হ্যাঁ, একদম ইমেজ প্রসেসিং দিয়েও সেম কাজটা করা যায়। কিরকম ভাবে জানেন? একটা মোবাইল ক্যামেরা, ফ্রন্ট ক্যামেরা অন করুন, মুখটা দেখুন, এইবারে মুখের এই যে ব্লাড ভেসেলের যে নড়াচড়া, এখান থেকে হার্ট রেট রেকর্ড করা যায়। এরকম অ্যাপই রয়েছে, ফ্রিতে কি বলতে পারবো না, বাট আমি জানি এরকম অ্যাপ রয়েছে, আমি নিজে ইউজ করেছি। ওই যে একটা গর্ত থাকবে, ওই গর্তের মধ্যে মুখটা আপনাকে ফিক্স করতে হবে, ও আপনার ফেসিয়াল এটা নেবে, এই যে ব্লাড ভেসেল এইখান থেকে রক্তের চলাচলটা মেপে হার্ট রেট মাপবে। আর হার্ট রেটটা পেয়ে গেলেন মানেই আপনি সেখান থেকে ইমোশন ডিটেক্ট করতে পারেন। কিন্তু মুশকিল হচ্ছে এটা আপনি লং টার্ম করতে পারবেন।
হ্যাঁ, আপনারা করেছেন, মানে আপনার কাজে কি এটা করা যায়? মানে এটাকে একটা অ্যাডেড যদি একটা মানে এটাকে কোরিলেট করে আপনার রেজাল্টগুলোকে আরো শার্প করার কি কোনো পসিবিলিটি আছে? মানে both of them go together, হ্যাঁ, মানে সেটা বলছি।
একদম করাই যায়, কিন্তু দেখুন, মানে অনেকজন লোক যদি একই সঙ্গে একই টপিকের উপর কাজ করে, তখন না কাজটা ছড়িয়ে দেওয়া যায়। কিন্তু এই টপিকটা আমি একাই তো করছি, আর আমার আশেপাশে সেরকম কেউ নেই।
অ্যাকচুয়ালি ইমোশনের কথা বলছেন বোধহয়।
ওকে, ফাইন।
ইমোশনের সাথে বোধহয় সেটাই বলতে চাইছি।
আরেকটা ছোট কোয়েশ্চেন, সেটা হচ্ছে আপনি যে বলছিলেন যে রিস্ট ওয়াচে সারা বছর ধরে একটা রিস্ট ওয়াচ পরে ডেটা কালেক্ট করতে পারে, সো দ্যাট উড বি এন্টেলিং আ লট অফ ডেটা, রাইট? বিগ ডেটা,
প্রচুর,
ওভার আ লং পিরিয়ড অফ টাইম। তো obviously become more into the picture.
হ্যাঁ, মানে দেখুন, কি বলে, ডেটা রেকর্ড করছেন, হ্যাঁ, ওই ঘড়ির মধ্যে মেমোরি সাইজ খুবই কম, কিন্তু
সেটা ক্লাউডে হয়তো পাঠিয়ে দিচ্ছে,
বা
ক্লাউডে পাঠিয়ে দিচ্ছে,
কম্পিউটারে ট্রান্সফার করে। হ্যাঁ, এই মেশিন লার্নিং যেগুলো করছে সেগুলো তো ওই ডিপ লার্নিং টেকনিক ইউজ করেছি, কিন্তু ডিপ লার্নিং এর অসুবিধাটা কি জানেন? মানে অসুবিধা না, মানে এটা কি আমি বলবো বুঝতে পারছি না। ডিপ লার্নিং একটা ব্ল্যাক বক্স, আমি নিজে ইউজ করেছি। ও বলছে কিচ্ছু লাগবে না, এই সিগন্যাল প্রসেসিং, নয়েজ ডিনয়েজিং কিচ্ছু করতে হবে না, আপনি ওকে বলে দিন এইখানে এইটা আছে, ও আপনাকে আউটপুট দিয়ে দেবে। ভেতরে কি হচ্ছে কিচ্ছু জানেন না আপনি। এবার দেখুন, ভেতরে কি হচ্ছে কিছুই জানি না, তাহলে আমরা রিসার্চটা করে লাভ কি? সবই ওই ডিপ লার্নিং এ ভরবো আর আউটপুট পাবো। কিন্তু প্রবলেম যেটা হচ্ছে, আমাদের মেডিকেল রিসার্চে এইটা দিয়ে আপনি পেপার খাওয়াতে পারবেন, কোনো অসুবিধা নেই, কিন্তু এইটাকে আপনি রিয়েল টাইম ইমপ্লিমেন্ট করতে পারবেন না। কারণ একজন ডাক্তারকে আপনি বলবেন, দেখুন এই ইসিজি দেখে বলছি আমি আপনার হার্ট অ্যাটাক হয়েছে বা মায়োকার্ডিয়াল ইনফেকশন হয়েছে, ডক্টর বলবে তুমি কি করে বলছো? না, ওটা আমি জানি না, ও ভেতরে মেশিন লার্নিং কমিউনিটি অ্যাকসেপ্ট করবে না। ওইখানে যখন আপনি এসভিডি বা কোনো ক্লাসিক্যাল মেশিন লার্নিং টেকনিক অ্যাপ্লাই করবেন, যার প্রপার এক্সপ্লেনেশন রয়েছে, যে একদম আপনি অঙ্ক কষে বলতে পারছেন, মানে আপনি পারবেন, হ্যাঁ, অঙ্ক কষাটা সব সময় সম্ভব নয়, মানে যদি ইচ্ছা করেন করতে পারবেন, তার একটা সলিড এক্সপ্লেনেশন আছে, সেটা অনেক বেশি অ্যাকসেপ্টেড ডক্টরদের কাছে। কিন্তু ওই ডিপ লার্নিং কি হচ্ছে ভেতরে জানি না, সিগন্যাল ভরে দিলাম, আউটপুট পেয়ে গেলাম, সেটা অন্যান্য যেখানে হিউম্যান লাইফ কনসার্ন নয় সেই সমস্ত ক্ষেত্রে অ্যাকসেপ্টেড, বায়োমেডিক্যাল সিগন্যাল প্রসেসিং একটু ডিফিকাল্ট
you.
এস্টাবলিশ করা। ধন্যবাদ।
Thank you. Huh? Your answer is very satisfactory. I'm satisfied. Thank you.
থ্যাংক ইউ,
So-
থ্যাংক ইউ।
সৌরভ, একটা কোশ্চেন একটু ছিল।
হ্যাঁ
হ্যালো?
ম্যাডাম, হ্যাঁ বলুন। হ্যাঁ হ্যাঁ ম্যাডাম, হ্যাঁ শুনতে পাচ্ছি, বলুন।
হ্যালো,
হ্যাঁ স্যার,
হ্যাঁ
ম্যাডাম
সৌরভ,
শুনতে পাচ্ছি।
বলছি
হ্যাঁ
যে
হ্যাঁ
কালার ইসিজি নিয়ে যেটা বললে, হ্যাঁ
হ্যাঁ
কালার ইসিজি নিয়ে যেটা বললে, ওখানে ওই কালার ইসিজির জন্য যে ইমেজটা যেটা জেনারেটেড হচ্ছে, সেখানে
হ্যাঁ।
ভ্যালুগুলো কি করে মানে ইমপ্লিমেন্টেড করা হচ্ছে?
আচ্ছা ম্যাডাম, আমি আমি একদম পুরোটা আপনাকে
পিক্সেল
একদম
ভ্যালুগুলো,
বলছি খালি। হ্যাঁ হ্যাঁ, ওখানে ওই প্রতিটা পিক্সেল কিন্তু এক একটা কিউআরএস কমপ্লেক্সকে রিপ্রেজেন্ট করছে ইন ফিচার ডোমেন। এই ফিচারটা ফ্রিকোয়েন্সি ডোমেনে হতে পারে, স্ট্যাটিস্টিক্যাল, মানে আমি একদম আপনাকে বলছি না, কারণ এটা না এখন ওই পেটেন্টটায় পেন্ডিং রয়েছে, ফলে আমি একদম ডিটেলসটা দিচ্ছি না, শুধু বলছি ওটা তো একটা আরজিবি, ওই আরজিবি ইমেজটার আর জি আর বি প্রত্যেকটা ভ্যালু কিন্তু ওই স্ট্যাটিস্টিক্যাল ডোমেন বা ফ্রিকোয়েন্সি ডোমেনে একটা ফিচার থেকে নিয়ে তৈরি হচ্ছে। আর দেখা গেছে যদি নর্মাল ইসিজি হয়, নর্মাল ইসিজির যদি ছবিটা তৈরি করেন, দেখবেন একটা সুন্দর কালার আসবে, একদম মানে একই কালার চারিদিকে রয়েছে। কিন্তু যখন এরকম একটা ছবি দেখবেন,
পিক্সেল ভ্যালুগুলো এক হয়ে যাচ্ছে,
মোরলেস, হ্যাঁ সেটা ভ্যারি করে, মানে নিঃশ্বাস প্রশ্বাসের সঙ্গে ওই হাইটটা বাড়া কমা করলে কিছু চেঞ্জ হয়, বাট এতটাও চেঞ্জ করে না যে আপনার কাছে স্যালিয়েন্ট হয়ে যায়। আপনি জানেন হয়তো স্যালিয়েন্সি ডিটেকশন একটা রিসেন্ট ভীষণ হট টপিক ইন ইমেজ প্রসেসিং ডোমেন, যেটা বায়োমেডিক্যাল সিগন্যাল এখনো ইউজ হয়নি। এবারে যখনই ওরম একটা ছবি দেখবেন যে সবকটা নর্মাল, হঠাৎ করে একটা পিক্সেল খুব ব্রাইট, খুব জল করছে, আমাদের আই কিন্তু প্রথমে ওখানেই যাবে। তো এবারে আই ক্যাচিং ব্যাপারটাকে ডিটেক্ট করতে হবে ইন স্যালিয়েন্সি ডোমেন থ্রু ইমেজ প্রসেসিং। সেটা যদি করতে পারি, ফার্স্ট অফ অল আমার কোনো মেশিন লার্নিং লাগলো না, শুধুমাত্র সিগন্যাল প্রসেসিং, এবং মানুষের বোধগম্য হলো, যে ব্যাটা কিচ্ছু জানে না, শুধুমাত্র ওই একটা দামি ঘড়ি পড়েছে, সেও বুঝতে পারে আমার কি রোগ হয়েছে, তো ডাক্তারের কাছে যেতেই হবে না, 1-2 সপ্তাহ ওয়েট করবো, সেটা কিন্তু সে নিজেই ডিসাইড করতে পারবে। আর একটা সুবিধা, আমাদের দেশে একটা সুবিধা বলবো, যে আপনার যদি কোনো শরীর খারাপ হয়, ঠাকুর করে কারুর না হোক, কোথাও না কোথাও আপনি অ্যাডমিটেড হবেনই হবেন আপনার যদি কোনো অসুখ হয়। ম্যাডাম আপনি হয়তো নিশ্চয়ই জানেন, এই দেশগুলোতে না মেডিকেল সিস্টেম খুব উন্নত, কিন্তু মেরে দিয়েছে একটা জায়গায়, আপনার যাই হোক যতক্ষণ না মরে যাচ্ছেন ততক্ষণ আপনাকে ডাক্তার দেখবেন, ইমার্জেন্সি ধ্যান দেবে না, 1000 লোক আপনার পিছনে লাইনে পড়ে রয়েছে, দেখার লোক নেই, একটা ডাক্তার নেই, যে কটা লোক রয়েছে ওই দেখছে একটা করে, মানে খুব যন্ত্রণা কিন্তু এখানে হেলথ কেয়ার সিস্টেম। তার জন্য যদি আপনি নিজেই, মানে মানুষ যদি নিজেই অনেকটা অন্তত কার্ডিয়াক হেলথটা বিচার করতে পারে, তাহলে ডাক্তারের কাছে ভিড় করে লাভ দেখি।
ওকে, ভেরি গুড আইডিয়া, আমার দেখে খুব ভালো লাগলো এটা, মানে সেই জন্য তোমায় জিজ্ঞাসা করলাম আর কি।
হ্যাঁ ম্যাডাম, অ্যাকচুয়ালি ওইটা মানে নেই, এটা আমরা পাইনি কখনো, যার জন্য ওইটা আমরা ওই পেটেন্টটার জন্য অ্যাপ্লাই করেছি, দেখা যাক কি হয়, দেখা যাক।
ওকে, থ্যাংক ইউ।
আমার প্রণাম নেবেন ম্যাডাম, ভালো দিন, কথা
হ্যাঁ,
হয়নি।
ওকে, তোমার সাথে পরে কথা হবে।
নিশ্চয়ই। আচ্ছা, আমি অ্যাকচুয়ালি ক্যান স্টেগানোগ্রাফি বি ইউজ টু কনসিল ইমেজ? অবশ্যই, ভিডিও অ্যান্ড অডিও সমস্ত ডোমেনে হয়, ইনফ্যাক্ট ইমেজেই বেশি হয়। ওই ইমেজে ছবিটা এনক্রিপ্ট করা, তার ছবির মধ্যে ঢুকিয়ে দেওয়া, যেটাকে ওয়াটার মার্কিং বলে। কিন্তু ইমেজের সুবিধাটা যেটা হয়, যে ইমেজের একটুখানি পার্ট যদি একটু ডিস্টর্ট হয়ে যায় না, খুব একটা অসুবিধা হয় না। ধরুন একটা কোনায়, একদম একটা ডান দিকের বা বাঁ দিকের কোনায় আপনি ইনফরমেশনটা রেখে দিলেন জল ছবি করে, যেটাকে বলা হয় হলো, কি বলে ওটাকে, কি একটা বলে বেশ, ওইটাকে ওরকম খুব অসুবিধা। হ্যাঁ ওয়াটার মার্কিং, আমি ভুলে গেছিলাম টার্মটা, খুব একটা অসুবিধা। হ্যাঁ, কিন্তু বায়োমেডিক্যাল সিগন্যালে যদি এটা করতে যান, এবং তাতে যদি দেখা যায় অ্যাবনর্মালটা নর্মাল হয়ে গেছে, বা একটা হার্ট অ্যাটাকের ট্যাবলেট দিয়ে বসে থাকবে, মানুষটা হয়তো ছিল সুস্থ, গেল মরে, এরকম হতে পারে। তো ওইগুলো খুব মাথায় রাখতে হয় আর কি।
Okay, I hope questions are finished, and we have our speaker waiting. So, thank you to
Thank you
excellent
so much.
presentation and opening a very new horizon of research to us. Actually, you are quite correct. As today itself, I was talking with one of my students who is working on machine learning, and he was just telling that deep learning is just a black box, and probably nobody who works with deep learning know what is going inside. Actually, nobody interested with the very complex mathematics that deep learning system has. So medical system cannot be left upon the chances. That's what you were talking, and you were perfectly all right. Medical system cannot be taken on chances. If anything goes wrong, say, human life can be in danger. So, I wish your patent get finalized, and we will be proud of this. And with this, I thank you, and I would welcome our next speaker, Dr. Uttam Manna. So, let me be just very formal to introduce Dr. Manna. Uttam Manna has joined the Illinois State faculty as an assistant professor of physics in fall 2016. He holds a PhD in experimental physics from Trinity College, Dublin, Ireland. Before arriving to Illinois State, he worked as a postdoctoral research scientist at the James Franck Institute at the University of Chicago and the Department of Applied Physics and Applied Mathematics at Columbia University. Dr. Manna has got his BSc in Electronic Science degree from Panchkuda Vanwali College under Vidyasagar University, and he has pursued his MSc from the University. I would like to request Dr. Manna to start and enlighten us about his research and his journey, and let us know what electronic science can make, can actually mold up a person who is studying electronic science. What do you, Dr. Manna?
Yeah, just a second. Oops. Can you see my screen now?
Yeah, it is clear. Nanophotonics and alternative to nanophotonics.
You can see the screen, right?
Yeah.
Okay. So you know, like, no, I was listening to the conversation, you know, and his name is Saurabh, right? I think he's doing very well, and yeah. So, and actually, so you know, like, I have not interacted with like our junior students for a long time. So I actually finished my BSc in 2001, so almost like 20 years ago. And I mean, like, I did not know that we have a society called like Electronic Science Society of India existed, actually, you know. And I mean, it's a great initiative by, I don't know, Ayan and Prasenjit. I have been talking to them. And I'm pretty sure many of you have also kind of actively participating. And I mean, this is a great initiative, and you can provide all the information. And I really commend your efforts. And I really wish, you know, when I started my journey, you know, I passed high school in 1998. And when I decided to study electronic science, you know, we had a platform like this, you know. So I really like to applaud your effort. Okay, so now about my presentation. So I'll talk about dielectric nanophotonics as an alternative to nanoplasmonics, and I'm hoping I should be done by like 35 minutes. And then after that, you know, I'll just briefly tell you like how I have come through the ranks. And actually, my goal is not to show off like what I have done, you know, but actually, I really hope it will like you know, make some of our students, you know, understand that actually anything is possible, you know. Yeah, I mean, and so that's the motivation of describing my journey. And another point I would like to mention that so my research is so I'm in a physics department, you know. Even though I had a BSc in electronic science and MSc, but in the US people don't really care about your degrees, you know. So can you do the task, you know, can you do the work? So if you are able to do the work, then it doesn't matter what degree you have, you know. So I'm in physics department, and so my research is very basic physics, you know, and there is no apparent like practical application right as of now, you know. We are in very fundamental physics studying, you know. So that is something I wanted to give you some heads up. Okay, and also, you know, I mean, so I teach one like a general education class where I have like 150 undergraduate students, and because of the current situation, all of our like classes are online, and I do really encourage everyone to keep your video on. I know there are circumstances might not allow it, you know, and I mean, many of you may be sitting like this at home. But I mean, this is a much better option that we have compared to the healthcare workers. You know, they are spending like 8 hours a day in a COVID ward where they are like, you know. So this is a much better choice. We are able to do our work from home, you know, and we should not really care about how our background looks. So please consider having your videos on and try to have interaction, you know. Okay, so before I start, you know, like, so just like any class, actually, I try to give some perspective of like why you are doing things, you know. And so I'd like to start with giving some perspective of my research. And to do that, I'm going to ask you one or two questions. So I'll really appreciate if you can answer this question, you know. So the question is, what comes to your mind when you think about light? Anyone, please.
The famous
I mean,
the famous equation for the square.
Yeah, I mean, I'm looking for like something very simple, like the sun, right? Sun is just like light, like source of sunlight, right? And so light is. Sorry, I think your voice was breaking up. Can you please repeat one more time? I'm saying very simple. Light is a form of energy. Yeah. So basically, I'm talking about like sunlight, a source of energy. Like I think if you ask every physicist, I think probably everyone top 3 answer would be like a laser, you know. So laser is like which has changed the world, really, you know. And so if you don't know, this is the image at the left, you know, is the first laser made by Ted Myman, you know, in 1960. And if you look at the scale bar here, you know, the scale bar is about like 1 centimeter and the whole thing is like few centimeter, you know. And the image at the left, in the right, is today's nano lasers, you know. And if you look at the scale bar, it is in like some nanometer, like 44 nanometer or 500 nanometer in the nanometer range. So these are nano lasers, you know. And so the size of the lasers has shrunk by 7 orders of magnitude in about 80 years. You know, and so this has been possible because of advent of nanoplasmonics. So I don't know if you have heard the term plasmonics. So plasmonics is like a really kind of last 10-20 years, people have spent a lot of time, effort understanding various optical phenomena related to nanoplasmonics. You know, so this has been possible because of advent of nanoplasmonics. Now other stuff, I don't know if you know about this Harry Potter clock things, you know. So like if you put this coat on, you become invisible, you know. So the invisibility clock, like other applications like, you know, perfect lensing, like, you know, when we are trying to focus light with a lens, because of the diffraction, we can only focus light down to a limited spot. But if you can make metamaterials made of nanoplasmonic structures, you can actually focus light to like a very tiny spot without actually having a diffraction limit. So all these possibilities has been like proposed, and people have spent a lot of time and energy, billions of dollars, you know, and so far it has not been successful yet. And all this came from the advent of nanoplasmonics, you know. So what I'm going to tell you is that I'm going to describe what is nanoplasmonics in a nutshell, and then I'll describe what is the problem with nanoplasmonic structures. So actually nanoplasmonic structures are made of metal, you know, and metals are very lossy, you know, so I'll discuss about that. And then I'll investigate, can we use high refractive index dielectric nanostructures? Instead of metal, can we use dielectric nanostructures as an alternative nanoplasmonic structure? You know, that is kind of the title of my talk. And then I'll briefly tell you some results, some experiments that we did in our lab on excitation of non-radiating anapole states in silicon nanosphere. So I'll show you some interesting results about that, you know, and then conclusions. Okay, so what is nanoplasmonics? Nanoplasmonics in a nutshell, okay? Now, just like the way I did ask you one question at the beginning, so let me ask you another question. Can you think of a way to confine an electromagnetic wave? The simplest way, can you please think of or come up with an idea that one can actually confine an electromagnetic wave? Oopsie, sorry. Anyone, please. So the simplest way one can actually confine electromagnetic wave is a two-piece of plane mirror, right? So if you have a mirror, and then if you somehow can send light between it, and then you can confine an electromagnetic wave between these two mirrors. So in optics and photonics term, this is called an optical cavity. You know, so you can have your light beam going back and forth between these two mirrors, and during that process they will interfere, and as a result you will get a standing wave. You know, so this is an optical cavity, and for the wave to exist within this cavity, the length of the cavity has to be an integral multiple of the half wavelength. So this is p is an integer, and lambda over 2 is your lambda is wavelength, and over 2, so half wavelength. So in other words, so if the say wavelength of light is like say 500 nanometer, then the length of this cavity has to be 250 nanometer. If it is smaller than that, then your wave will not exist. Okay. So I'm actually, you can hear me, right? Okay. Okay, so that's an optical cavity.
Yeah,
okay,
you're audible.
okay. And so then if you also examine, so now we know that electromagnetic waves are, you have the electric field and the magnetic field components and the direction of propagation. So they are orthogonal to each other, right? All of them are perpendicular to each other. And so if you look at the electric field component and the magnetic field component, they are actually 90 degrees out of phase. Okay, so if the maxima of one wave is the maxima of the electric field is the minima of the magnetic field, you know, and the vice versa. And so as I was telling you, so if you have a light of like say 500 nanometer, so the smallest distance or smallest volume that you can confine an electromagnetic wave is going to be 250 nanometer. Okay, and there is a term for that. This is called the diffraction limit. So you cannot focus a light beyond the diffraction limit, and for a visible light with 500 nanometer wavelength, this length is going to be about 250 nanometer. Okay, so classically or conventionally, by conventional means, in an optical cavity you cannot like confine your light beyond this limit. So now the question is, can we actually confine the light beyond the diffraction limit by some other means, you know? And if we want to do that, we have to abandon two assumptions we just made. One is that the best confinement is provided by mirrors. So that is not going to be possible. We cannot use mirrors to confine light anymore. And another assumption that you have to reject is that the optical energy that is confined within the cavity is solely electromagnetic in nature. So the energy cannot be solely electromagnetic. So I'll talk about that in a minute. Okay, so the question we are trying to address now, can we confine light beyond the diffraction limit? Now in our high school, actually in high school, I believe I studied this in my high school, and like students here in the US, actually they study in college, so the first year of college or university. So if you have a metal sphere, if you take a metal sphere and if you shine or illuminate this with a light, you know, so the electric field of the light will polarize the metal sphere, right? So it's called polarization of conducting sphere, right? So if you illuminate a metal nanoparticle with light, it has a lot of free electrons, And then as a result, the charges, the electrons and the positive and the nucleus, they will be separated from each other. The center of mass will not be at the same place, and as a result, you get a polarization of light. Now we did study this for a static light, like the light which does not change as a function of time. So instead, if we illuminate a metal nanosphere with an alternating light field, like you have like a changing light field, then what we get is an oscillation of the electron clouds. So the electron clouds within the sphere goes back and forth, and they have a frequency called plasma frequency. And when the excitation frequency match with your plasma frequency of the electrons, then you get very large enhancement of the electric field at the surface of these metal nanoparticles. So this is what is called a surface plasmon resonance, or localized surface plasmon resonance, if you have heard this term. So basically we are illuminating metal sphere with light, and at a particular frequency the electric field is enhanced. Okay, now two things. One is, in this case, if you illuminate a metal nanoparticle, then the optical fields are confined within the nanoscale, and their spatial distribution scales with system size. What I mean is that if your metal nanoparticle was like say 50 nanometer, then actually your electric field is confined within that volume. So in this way, by illuminating a metal sphere with light, you can confine the electromagnetic wave way beyond the diffraction limit. So this is at the heart of the nanoplasmonics, this physical picture, that we will take some metal particles and illuminate with light and confine the electromagnetic field to a very, very smaller spot. So this is the physical picture at the heart of nanoplasmonics. All the people, thousands of people working in the field of nanoplasmonics, so their basic idea is this. And so once you can do that, you can do a lot of things. Like, for example, you can get surface enhanced Raman scattering. You can have a lot of metal sphere, and then you can put some molecule there, and then this molecule can interact with that enhanced field, and as a result, you can get an enhanced Raman signal. You can get fluorescence enhancement, like Purcell effect, if you're familiar with. So the fluorescence rate can be actually controlled by putting some fluorescent material near to these plasmonic structures. Then you can optically trap particle using these nanoplasmonic structures. You can use them in solar cell. They can help you absorb more light in certain frequencies, and so on. And you can create optical metamaterials, which can give you like cloaking and those kind of stuff.
Dr. Manna, can you please make the presentation full screen so that we can, some people are watching on mobile phone.
I see. So I'll remove
thank
the
you so much.
full screen. Okay, sure. Okay, cool. Okay, so yeah, so actually I have a lot of animation, so I don't know if I can run the animation if I don't have the full screen. So I don't know. Let's see. Okay, so so these are the potential applications of nanoplasmonics that you can get. And as you can see, like these papers, like the Nature Photonics and the Nature Materials or Science, like these are the best journals you can publish, and so these have been very high profile papers, published in this nanoplasmonics in last 10-20 years, and by leading scientists in the world. I'm talking about, people in like Harvard, MIT, or Caltech, or whatever you can think of, And so this graph shows the number of articles published in nanoplasmonics every year. It started about 1960, and by 2015, people are publishing like 10,000 papers per year. And these are different milestones along the way. Like for example, near field optical microscopy. And then like metamaterials, perfect lens. So these are milestones which has been achieved so far. Like at a very basic fundamental level, and people are publishing like 10,000 papers per year until like last year. However, there are very few practical applications. And like there are some, I think, applications in biosensing and things like that, but not many. And the reason is the plasmonic structures are made of metals. You know, the metal, same metal where that helped us to confine the electromagnetic wave beyond the diffraction limit is actually is detriment for this particular purpose. So why is that? Now, if you remember, if you remember, I don't know if you remember the simple harmonic oscillator, the energy, you know, the mechanical energy of a simple harmonic oscillator, you know, it goes back and forth between your kinetic energy and the potential energy, right? Like if you have a spring which goes back and forth, then your total energy is a summation of your kinetic energy and potential energy, and so the total energy is always constant. And exactly same thing happens for an optical resonator, you know, just like an oscillator, mechanical oscillator. For an optical resonator, so what happens is the total electromagnetic energy, it bounces back and forth between your optical energy and the magnetic energy. You know, the electric field and the magnetic field, they're 90 degrees out of phase. So if you have the maximum electric energy, then there is no magnetic energy. And if you have the maximum magnetic energy, then there is no electric energy. You know, so it kind of goes back and forth. Now, when you confine electromagnetic wave to a very tiny spot, like with a length well below the half wavelength, like say 50 nanometer or 20 nanometer, you know, so then you have electric energy, but the magnetic energy cannot keep up with it anymore. So the magnetic energy is too small. So then you have an unstable system. So in that way, you could not have the total energy to be constant. So to take care of that, what happens is we have to introduce the free carriers like the electrons. We have a lot of electrons in metal, right? Free electrons into the system. And once that happens, then your total energy is a summation of the optical energy as well as your mechanical energy. Here in this will be like kinetic energy of the electrons. Now, as soon as you put the electrons into the picture, then things get very bad. Now, we all know that, you know, the optical response of free electron can be described by Drude model, you know, and these electrons basically, you know, they are moving around the lattice sides and they collide with each other, and there is a relaxation time, you know, which is basically the ratio of the mean free path over the velocity of the electrons is in the order of 10 femtosecond, or or like 10 to the power negative 15 second. So what this basically means is that the energy is lost at this rate. You know, so you have a plasmonic system where you are illuminating metal nanospheres with light, and you have this large enhancement of the electromagnetic field. You can do a lot of cool things with that, but the problem is there is not enough time for you to extract all those. You know, so the electrons are colliding with each other and the lattice sides, and so as a result, the energy is lost very fast in femtosecond. So this is the problem with nanoplasmonic system. So they are lossy. So metals are lossy. That's the problem. And this leads to this, you know. So in psychology, there is a very well-known Kubler-Ross grief cycle. You know, people go through different stages of grief. You know, like you have normal functioning, then you try to deny stuff, then you get angry, you know, you detach yourself, you know, then you try to have a dialogue, and then you finally accept whatever the life is, you know, and then you return to your meaningful life. Now, believe me or not, this diagram has been published in a peer-reviewed article in Advanced Optics and Photonics. You know, so people working in the field of nanoplasmonics, they actually go through these emotions. You know, and so and this is true. You know, I used to work in nanoplasmonics, so I have been through this. So now, if you look at the bottom, that there is called detachment, and the proposal is, should we go back to dielectrics? You know. And so last about 5 years, or like 5 to 8 years, there is a lot of interest in dielectric nanostructures as an alternative to nanoplasmonics. So which I'm going to talk about next. So this brings me to my third part of my presentation, which is, can we use high index dielectric nanostructures as an alternative? So far, do you have any question? Please stop me. You know, I'm happy to be interrupted, and if you have any question, please let me know. I'll happy to answer, or we can wait until the end as well. I don't know. Okay, so now let's investigate, can we use dielectric as an alternative to nanoplasmonics? So on this slide I have to animate because it's all over the place. Okay, now this is from like internet, I got this picture. So basically for a dielectric, what happens is, in a metal you have a lot of free electrons, you have electron cloud, but in dielectric those electrons are bound to nucleus. So you have bound electrons. You know, when you polarize a dielectric, you have polarization due to the bound electrons which are not free and they are attached to specific nucleus. That's the difference between a metal and a dielectric, right? And so, and I don't know if you have taken, all of you have taken the introduction to electrodynamics. You know, this is like from chapter 4 of Griffith. You know, you can express the electric field inside a dielectric as a function of surface and volume bound charges, and this is the expression for potential. And once you can find the potential, you can take the gradient of the potential to find the electric field. And so then what you get is basically like the truth, like the summary is that in a plasmonic system or a metal system, you get large electric field enhancement due to the free electron, but in a dielectric all you get is because of the bound electrons. You know, so you get similar enhancement of the electric field, but that is because of the bound electrons. And this is the different relaxation process in dielectrics. And you can see that the dipolar relaxation process, which is comparable to the metals, is in the 10 to the power 9 hertz, which is actually in the nanosecond range. You know, so it's much slower, like 6 orders of magnitude slower, the relaxation process in dielectrics compared to like metal. And so in principle, dielectric can help you minimize losses, you know. And so in principle, we can use that. Now, what about their optical performance? Now, if you have a very small particle like a metal nanoparticle, you know, we can express the scattering from a small particle in terms of Rayleigh scattering, right? And the Rayleigh scattering mostly depend on the Q, which is a structure parameter, and which is the ratio of the radius of the particles and the wavelength of light, you know. And for your structure parameter, if it is very much smaller than 1 and the refractive index is between 1 and 2, then most of the scattering that you get is from dipole excitation. You know, you just get a dipolar excitation, and this is a typical scattering spectra of a gold nanoparticle with various diameter. You know, and so all this peak that we get, like for a 50 nanometer gold particle to 100 nanometer, we all get like a strong peak at the visible around 550 nanometer, and this is because of the excitation of the dipoles within the metal nanoparticle. But on the other hand, you know, so I'm going to have to animate this again. On the other hand, for dielectrics, what happens is, because the enhancement of the electric field comes from the bound electrons. So what we end up getting is that we have a circulating current within the structure. You know, and when you have a circulating current, then we know that Maxwell Faraday's law of induction tells us that if you have a curl of electric field, that gives a time varying magnetic field. So in addition to the dipolar excitation due to the bound electrons, we also get magnetic resonance or magnetic response, you know, because of this curl of the electric field within the dielectric nanoparticles. So for metal, you know, we only get response due to the electric dipolar resonances. But in dielectric nanoparticles, in addition to the electric dipolar resonances, we also get response due to the magnetic resonance, you know. And this is a calculation of scattering efficiency for metal and dielectric. And as you can see that for metal, we have electric dipole and electric quadrupole. This is the scattering. And for dielectrics, we have electric dipole, magnetic dipole, and so on. Okay, so, and one can express this in terms of misscattering. I don't know if you're familiar with it, but I'm not going into details of it. So the conclusion from this slide is that, so for the dielectric particles not only give you large enhancement of the electric field at the surface, but also it gives you like the possibility of manipulating the magnetic resonance, which is not there in metal nanoparticles. Okay. And so this is called the multiple zoo. These are various multiples that you can excite in a dielectric nanoparticle. So the first row, so are dipoles. It can be electric dipoles, magnetic dipoles, or toroidal dipoles. I'll talk about the toroidal dipole in a minute. And you can have quadruples. They can be electric, magnetic, or toroidal as well. And you can also have octopoles and so on. Now, one interesting thing here to notice is that all the dipoles, like electric dipoles, magnetic dipoles, or toroidal dipoles, they have identical radiation pattern. When they're so these are the, like, when you are exciting them, they radiate in the far field, and this is the radiation pattern, like an antenna. Antenna has a radiation pattern, so it's like that. So that is something for you to note down that will be required later on. So these are the various kind of multiple you can excite in the structure, and this is the first experimental report of excitation of electric and magnetic resonances in silicon nanosphere. And you can see that at diameter 100 nanometer, you get a magnetic dipole, and at 140 nanometer diameter, you get magnetic dipole, electric dipole, and so on. Now, again, I should tell you that these spectra are taken at the single nanoparticle level. So that the image, the SEM image you see there, is the image of the identical or exact same nanoparticle whose scattering spectra is being presented here. And those color image is the optical microscope image. So these are presented, these are measured at a single nanoparticle level. Now, following this report, this was 2012, right? Following this report, a lot of papers have started coming about. One of them is like electric and magnetic field enhancement in the electric nanostructure, and then then there was surface enhanced Raman scattering using dielectric nanostructure. Also, like, one can use silicon as an antenna, and one can have a directional scattering as well from silicon. And nonlinear effects like third harmonic generation is also been detected, and so on. So there is a lot of interest coming right now as we speak, and so we'll have to see actually if it will apply. It can be extended heavily to applications on things like that. But there is a lot of interest in dielectric nanostructures. So this is an alternative kind of approach. So people are trying to explore. Now, the final part is, so I want to tell you something about that we did in my lab at Illinois State University. So this is something called excitation of non-radiating anapole states in silicon nanosphere. Now, what is anapole? So anapole is a Greek word. It means without poles, and so it means is that you have something which does not radiate or non-radiating. It does not have any pole, that's why it doesn't radiate. That's what the anapole means. Now, this term anapole was actually used by Yakov Eldovich in 1957 with regards to parity violation in nucleus. So he showed that by calculation he showed that spin half Dirac particles like nucleus has to have some anapole state for a stable configuration. And this was experimentally measured by Carl Wieman in University of Colorado, and for that he got a Nobel Prize actually, and so he made this anapole state. He measured the anapole state in cesium atoms, but those are static anapoles. But the electrodynamic anapoles, was in dielectric nanostructure was reported in 2015, like 5 years ago, and it was published in Nature Communications. So non-radiating anapole modes in dielectric nanoparticles. And so what is an anapole? Now, we have all kind of seen this picture. This is a toroid. Okay, so if you have a solenoid and if you carve the solenoid until the two ends meet, and then you have this poloidal current flowing on the surface of this toroid, and because of that you can get a toroidal response, right? And this B is the magnetic field that is created because of this poloidal current. And I think this also, we studied this in our high school, And so what happens is, for a dielectric nanosphere, or nanostructure, because of this current, displacement current that you're creating locally, And within the volume of the structure, in addition to the electric multipoles, electric dipoles, like, you know, like positive and negative, the electric dipoles, you also get this colloidal current flowing at the surface, and there gives you toroidal multipoles, you know. And so that it can be detected in a dielectric nanostructure. So you have electric dipole, magnetic dipole, as well as toroidal dipole in dielectric, which you do not get in a metal structure. Now imagine a situation. Now I did mention that the electric and the toroidal dipole has identical radiation pattern. Okay, so the exact same radiation pattern. Now somehow, if you can make the magnitude of the electric and the toroidal dipole equal to each other, so P is the electric dipole moment and T is the toroidal dipole moment. Okay, and if you can make their magnitude equal to each other, and if they are 180 degree out of phase, then you can actually cancel out the scattering completely because of the destructive interference between the radiation of electric dipole and toroidal dipole. You know, and if you can do that, then you end up having a situation where you have a local field excitation of the dielectric nanosphere or nanostructures locally, but it does not radiate in the far field. You know, so this configuration is basically the configuration of anapole states. So how can we detect anapole state? Now this is the spectra that I showed you before a few slides back. You know, if you excite a dielectric nanoparticle with like 200 nanometer diameter, you get magnetic dipole, electric dipole, magnetic quadrupole. So this spectra is very complex. You know, it's very difficult to understand what is from what. So in addition to the electric modes, you have these adjacent magnetic modes are also excited, you know. And that's why it is very difficult to detect anapole states in dielectric nanospheres. And so this is not a good way to detect anapole state. So to conclude, the spherical geometry under plane wave illumination is not suitable for detecting anapole states. So if you take a nanosphere, and then if you're trying to illuminate with a plane wave, then you cannot detect anapole state efficiently, you know. So what they did was, the group who actually reported this for the first time, so they did was they took a silicon nano disk, like this is 1 nano disk and the 200 nanometer level, you know. So they took a nano disk, and this nano disk, because of the shape and size of the disk, so they have like only contribution from the electric mode. So there is no magnetic mode within the measurement window. And from there, so they did two measurements. One is they measured the scattering, and they found that there is pronounced dip in the scattering spectra. Okay, and then at the same time, they measured the local field by a technique called near field scanning electron optical microscope, and they correlated their result and did some calculation, and then they found out that this dip is because of the destructive interference between the electric and the toroidal dipoles. And from there, they claim that you know, so this is an anapole excitation of anapoles. Now the question is, you know, this has been done in nano disk. Now these disks are very difficult to make, so you need a complex lithography process to make these kind of disks, you know. So the next logical question would be to ask, like, is it possible to excite anapoles without relying on design of complex nanostructures such as nanodisk? Like, can we do it in a simpler structure like, say, a nanosphere? So that is the question we tried to address in our lab, you know. So we took an approach called beam engineering, and or it's also known as a vector beam spectroscopy. So we developed a technique called vector beam spectroscopy, you know. And so the vector beams are different from like a linear beam, like linear or circularly polarized light. So those are the light that we are familiar with. But you can create other beams like azimuthally or radially polarized light, you know. And if you excite your structure with those kind of beams, you can actually have very specific mode excited within the structure, you know. Like, for example, if you excite a nanosphere with azimuthally polarized light, you can actually only excite the magnetic dipoles, And if you excite your structure with a radially polarized light, you can excite only the electric modes. I'm not going into details of these modes. And then we did some calculation and showed that, if you illuminate a metal nanosphere, dielectric nanosphere with a radially polarized beam, then you can actually excite the toroidal dipoles. And then we did some experiment and measured the scattering spectra at the single nanoparticle level. And you can see that at some wavelength, at around 500 nanometer for radially polarized light, the scattering intensity almost goes to 0. And we also did some calculation by doing some multipolar decomposition, and then from there we found that at that particular wavelength, the magnitude of the electric and the toroidal dipole are equal to each other, and they're out of phase as well. And from there we concluded that we have excited anapole state in silicon nanosphere. And we also found that if you excite an anapole state within the dielectric nanosphere, then you can actually localize energy 6 times greater for radial beam compared to your linear beams. And there are some papers about potential applications of like anapole states, like anapole nano laser, or you can have a high Q factor of anapole state, and also you can have like broadband absorption and things like that. And so to conclude, so just to give you the overview of the stuff that I talked about in like a one slide. So we know that we can use metal nanoparticle to confine light at the nanoscale beyond the diffraction limit. However, metals are lossy, so there is a problem. But we can use dielectrics as a possible alternative. And then I showed that we can use vector beam or azimuthally or radially polarized beam to actually excite various modes within dielectric nanosphere. And then I also showed that we can detect anapole states within dielectric nanosphere. And so this is actually like a virtual tour of my lab that we have here. So this is like optics lab that I built at ISU from scratch. So this is an optical microscope, and you have these optical components. So this is all we need to do all this research that I talked about. And this is like one of my students working in the lab. He's trying to align the optical components. And so this is one of my undergrad student. Actually, he's working on taking some data as you speak. And so this the result that I just talked about was published at the beginning of the year in the journal called Physical Review Letters. So this is like perhaps the most prestigious journal in physics that one could publish. And as you can see that my undergrad students are also being co-authors. So this work, like my undergraduate students are actually participating in this work that I'm doing. And also our work came at the cover of the Journal of Applied Physics. This was a cover article which was selected in the Journal of Applied Physics as well. And so this is like my students presenting at conferences and so on. So this is a group. So that's all about my research. Now, also I did promise to tell you some story about my journey, right? So now, before I tell that, as I didn't mention, my goal is not to brag about what I have done or show off what I have done. I really, really appreciate and respect all my friends actually who did start. Like we are the first batch of electronic science in Panchkula Banwali College, and most of us actually been able to go on and do something in life, and everybody's journey is unique, and they have and they have their own story to tell. I'm pretty sure about that. And all of them have gone on and to do great things in life, and so I really respect that. And so this is like my own story. And when I was a kid, like when in college, I would call myself a kid. Like when I was a kid, I used to come across as like a very arrogant person, and so this is like, but now like I'm as humble as I have ever been. You know, so the story I'm trying to share with you, you know, just to like being like, you know, like a, so that I can give you some perspective, you know. That's all. Now, going back to 98, actually, you will not believe, this is the scanned copy of my higher secondary mark sheet, you know. And I got like 65% in higher secondary. You know, we know all the usual suspected reasons, right? We had cricket and we had girlfriend and, you know, all those sort of things, right, in school, right? And so even though like we had potential to do well, but it, of course, that did not reflect in our results, and hence the struggle started, right? And so I mean, basically, I didn't get anywhere in a respectable college, you know. And at that time, Panchkula started this electronic science, and they were at that time, 98, they were asking for like 25,000 rupees. You know, that was a big deal, you know, for my family. You know, I remember those days. And so, I mean, the burning question was like, should we study electronics? You know, I mean, what are we going to do studying electronics? I mean, I remember after when we were contemplating should we study electronics, we took a train ride to Mednipur, you know, Midnapur, and then because we wanted to meet Professor Montu Das, you know, MD at Pasco, and so, you know, he used to like he was famous for like tutoring physics students, and we were hoping that he would give us some idea. However, the problem was like, you know, we did not know his address. So what we did was we just went to Mednipur, you know, and we asked people around, and then we could not find his address, and we thought that we'll find him, like we'll research the whole town, you know, but we could not do it, and we had to come back without any information. However, the good thing was at that time, you know, we used to pretty much travel railways for free. You know, Mamtadi was the like railway minister at that time, you know. And we, even though it was illegal, we never paid any price for riding rails. You know, we used to create bawal whenever some TT used to ask for, you know, ticket, you know. And I remember, like, you know, I mean, actually, I was talking to Oyon the other day. You know, I could write a book about stuff, you know. But anyway, and so those are the questions. And then, like in the department, we have like constant demoralization, you know, from physics faculties and other everyone's, and everyone had their favorite students and stuff like that. And wherever we used to go, we used to create troubles, you know. People used to call like bawal bacha, basically, you know, like we were troublemakers. And no one actually counted on us, like that these people would actually grow up and do something in life. Nobody counted on us. And even my own very close relatives, like my uncles and so on, like basically খরচের খাতায় বলে না, খরচের খাতা দিয়ে দিয়েছে আমাদের, like বাপ 25,000 টাকা দিয়ে ভর্তি করেছে ইলেকট্রনিক্স, like আমার খরচের খাতায়, basically, you know. It's like this. No, I'm not joking, actually, this is like true, you know. Anyway, so then I did well enough, like in terms of the percentage of marks that I got, you know, to get into Jadavpur, you know, Jadavpur MSc. And so actually then, and the first year, you know, coming from Mednipur, like coming as a Tumpa to Jadavpur, it was a big deal, you know. I mean, I did not like, so the 1 year it took like to adjust, like how I'm going to survive in Calcutta, you know. And so and then in the final year of my master's, I was assigned my final year thesis master's project to Jadavpur, to the Electronics and Communication Engineering Department at Jadavpur University, you know. I mean, that is like one of the best departments we have in Bengal, right? And there I met two persons. One is Professor Hiranmay Saha. I don't know if you know him. Actually, he's a very well-known figure. And also Professor Dr. Utpal Ganguly, you know. So that actually changed my life completely, you know. And so, you know, at that time when I was doing my project, I used to teach the undergraduate BE students electronics labs, you know. That gave me a lot of confidence, like, you know, I can actually teach undergraduate BE electronics lab, who are the best students we have, you know, in Bengal. So that gave me a lot of confidence, and I did really try my best to do well during my research project, you know. And that actually opened up an opportunity for me to go to do a PhD in South Korea. It's called Sangungan University in South Korea, you know. However, that's like another story. So I spent 1 year there, and it was not a pleasant experience. You know, basically I was like treated as a labor and exploited, you know. And so it was very not a good experience. And then after like about 6 months I spent there, I decided, okay, so I think we have to move on. I have to find something else. However, in between all those struggles, I met people from like southern part of India. Like before that, I have never met anyone outside Bengal who are in my level, you know. And I met many people from southern part of India, like from Tamil Nadu, from Madurai, and so on. And so then, like, I was so much kind of abased that how little we knew from students from Bengal about the whole world, you know. I mean, when I was in Jadavpur, when people used to ask me, oh, where did you study? You know, I said in Jadavpur University, and people used to praise me like hell, and my collar used to go up, like, oh, I'm doing something, you know, I'm someone. You know, so that was the attitude, you know. But when I talked to these guys who are like same age, I was very, very surprised how much they knew. So this experience in South Korea actually opened my eyes to the whole world, you know. And I had access to computers, high-speed internets, and most importantly, actually food and shelter, which actually, you know, when I was in Jadavpur, I didn't, many times I didn't have money. I had spent like the entire day having like one meal, you know, that's the, like when Masi will come and cook at night, that's the meal I had, you know. So that's how, so I wanted to use that opportunity, you know. So there, during 1 year of my research, I did work on organic LEDs. You know, I actually published like 2 papers, you know, one in Thin Solid Film and another in Japanese Journal of Applied Physics. So once I got 2 papers as my with some research experience, then actually the entire world opened up to me. You know, as a graduate student, before if you want to do a PhD, if you have published 1 or 2 papers, then you are in demand. You know, you will get opportunities. You know, and so that brought me to Trinity College Dublin. You know. So this is actually the picture of Trinity College Dublin. It's like one of the most beautiful campus that you can get ever, you know. And at that time, Trinity College was like, and the world ranking was like top 50, you know. I got this opportunity, and so I went there and I did my PhD from 2005 to 2009. And it was in the Department of Electronics Engineering. However, my research was on liquid crystals, you know. So liquid crystal is basically experimental physics, soft matter physics. You know, that's when actually I started learning physics. You know, so I started learning my StatMech, which I ignored when I was a grad student. I only studied electronics, and so I thought that physics is not going to be useful for me. So then I started studying like statistical mechanics, classical mechanics, all by myself. You know, so একটা কথা আছে না, it's like চাপ পড়লে বাপ বলে, ওনা কথা আছে না একটা. It's like that, you know. I did not study it when I was in college or university, you know, when teachers were teaching it. And then when I did not have any option, then I took books from library and started reading those again, you know. And so during my PhD, I published like 12 papers, and some of the best physics journal you can publish, like Physical Review East, Applied Physics Letters, and all over the place, like left, right, center, you know. And so after that 12 paper, so then I wanted to do a postdoc. I wanted to come to US, you know, because everybody goes to US, right, to do stuff. So this is actually a bird's eye view of Columbia University campus. So this is the university campus, and that's actually the New York City, you know. So it's like, so this is the Columbia University is within, like, is right at the heart of New York City, you know. So I came there from 2009, and I stayed there until 2012. And during that time, I worked on quantum dot superlattice structures, you know. So we can grow these very tiny quantum dot multi-layer structures. And there I had like the time of my life, you know, like the New York City, and like the people there I met, I made lifelong friends with them. And also I did well in terms of publishing results. I again published like 5 papers in Applied Physics Letters, Journal of Applied Physics, so all the top journals, you know. Now in India, actually, we mostly know like few universities in US, you know, people who have not been visited US. One is like Harvard, we all know about Harvard, we know about MIT. These days, I think Stanford is getting a lot of attraction and stuff like that. But Columbia University is actually one of the premier institutions in the US. So this is actually the rank of national universities in the US. So you can see Columbia University right now is ranked number 3 in the US, after Princeton, Harvard, and then Columbia, you know, then actually MIT, Yale, and so on, you know. This is number 3 ranked university in the US right now. And actually, when I came to Columbia, I did not know much about it, you know. And so this is like total number of Nobel laureates by institution, you know, and Harvard has like 160, and you see Columbia University is number 6. It has 96 Nobel laureates, you know. And some of the notable alumni, you know, we know Barack Obama and Warren Buffett, they are alumni from Columbia University. Do you know the person in the left? Anyone? Who is the person on the left?
Excuse me, we can't view the slides you are talking about.
So which slide you are talking about?
Yeah, now I can see. It was stuck at one slide.
So I have some pictures of some notable alumni. Can you see it? Who is the picture on the left? So this is actually Dr. Baba Saheb Ambedkar, you know, he is the father of our, so he wrote the Constitution for India. Actually, he went to Columbia Law School as well, you know, and so on. So anyway, so then after 3 years of postdoc there, actually I went to University of Chicago, you know. So this is also close to the city of Chicago. I spent about 3.5 years there, and again I published like some of the premier journals in the world. And University of Chicago is also ranked very highly, like number 6 right now in the US, and it has like 100 Nobel laureates, you know. And these are some of the people actually has worked at University of Chicago. You know them, like Chandrasekhar, he got Nobel Prize because of his work at University of Chicago, you know. Fermi, Enrico Fermi, Heisenberg, Compton. So these people actually all work at University of Chicago Physics Department, you know. So I mean, you know, like, so the whole journey is like overwhelming, you know, and looking sometimes when I look back, like 2 decades back, you know, and like the journey that I have gone through, it seems really unreal for me, you know. And I have been extremely fortunate, like, you know, every step of the way, like what I wanted, what I really tried to get hard for, actually I have able to get it, you know, extremely fortunate, you know. And so, you know, some word of advice, you know, for you, if you want to go, like some words of advice, you know, not everyone is like Sachin Tendulkar, you know, not everyone is born with talent. You know, people like not everyone play like their first international match at the age of 16, you know. But you can have a good attitude, and you can have a fearless, you know, you can be fearless, you can make mistakes, learn from it, own it, you know. And at the same time, if you work very, very hard, you know, you will do things in life, you know. There is absolutely guarantee, you know. If you work very hard, of course sometimes it may not pay off, but at the end of the day it will pay off. Okay. And so have a good positive attitude and try to use the best opportunity you got, you know, all the time, rather than complaining about all the time. You know, if you focus on the opportunity that you got, I think you will do well. And actually, I had a pleasure of meeting Dr. Kalam at Trinity College Dublin, you know, when he visited. So this is so true for me. You know, he said that dreams is not what you see in sleep. That's not dream. This is something which does not let you sleep. Dream is something which does not let you sleep. Now, I cannot tell you how many nights, whole nights, I have not slept dreaming about what I will do next, or what I will do next day, you know, what I will do next week. You know, I had actually insomnia because I used to dream stuff while I was sleeping, because I wanted to do something, you know, the next day or the next week or the next year. I had goals, I had dreams, you know. So if you really want something badly, you know, in life, you can achieve it. So I really hope you take that message from my presentation. And so I'll stop there. And if you have any question, please let me know. And also I have this email address I have put up here, you know. So reach out to me. I'm really happy to help you in any way whatsoever, you know. And I'm fine to talk to you one on one. You know, if you want to kind of talk to me over Skype or like over Google Meet or Zoom, whatever you prefer, you know. So, and you can just send me an email and we can schedule time, and I'm happy to take time out and talk to you one on one if you need help. Okay, I'll stop there.
Okay. I have one question. I have one question, Pradhanjit.
Sure.
Hello?
Yes, sir.
Yeah, please. Yeah, go ahead.
You have talked about the nano dimension dielectrics structures But at the same time, you told that when it is within diffraction limit, the magnetic field is out, only electric energy and the mechanical energy will be there. So
Yeah.
how then it will be an electromagnetic wave? Always in an electromagnetic wave, electric field and magnetic fields are auxiliary way, they are associated. So this
Sure.
is
So
not
that is there.
please clear it to me.
Sure, that is there. So if you look at the electromagnetic, if you look at the, so this is how the configuration becomes. You know, if your structure is very small, so your electric field is like that, your magnetic field is like that. Okay, and so what happens is, so you have this electric energy, and then if you calculate the corresponding magnetic energy, so it is going to be very small, and the cavity is going to radiate the energy out. So in other words, your magnetic wave will not exist anymore unless you introduce some other means to conserve the energy, like electrons.
But you are talking a lot of magnetic resonances within these structures. If there is no magnetic field or etc., how
No,
the
so once you introduce the electrons into the system, then your energy can go back and forth between electric energy and the kinetic energy of the electrons.
And what is the output of laser, the power output of these nano laser in comparison to the surface plasmonic laser in actual practice?
So actually that's I think one should look at it in terms of like the efficiency, like the quantum efficiency, you know. So the total power is going to be very small, like few milliwatts maximum, you know.
Okay.
But if you look at the efficiency of these, are actually near field lasers, you know. These lasing happens in the near field, and so if you can couple efficiently this laser with a like a waveguide or something, you know, so then actually so the coupling is also a problem. Like it doesn't really couple well with waveguides and stuff. So these are near field lasers, but in terms of magnitude, it's like few milliwatts maximum, or even less than that. Actually, maybe microwatts or nanowatts. I don't know. But in terms of their efficiency, actually, they're very high. Like how much energy you're putting in and how much energy you're getting out.
And which is more cost effective?
So these are like, as I told you, these are like very fundamental stage, you know, like research stage, you know, and so these are made in labs with some lithography, you know, and stuff.
Okay,
but
okay,
if say one is selling them in the market, I don't know, like what would be the optimization of like large scale production and things like that.
Okay, thank you, Dr. Manna, for your nice talk.
Yeah, thank you. Yeah.
Any more questions?
Ayan had a question. Ayan
Yeah.
Pradhan had a question. Ayan is there? Ayan, are you there? Okay.
You can find the question of Ayan Pradhan at the chat box.
Okay. Is there any formulation to predict the dielectric constant and loss tangent variation with frequency? I mean, I mean, these dielectric materials are so well known. I mean, they have been studied like for over a century, you know. So I'm pretty sure there is like a calculation of how the dielectric constant of a special material, like a very common material like silicon, you know, changes as a function of frequency. Like I don't have the graph right now with me, but yeah, I'm pretty sure if you just Google it, you'll find it, you know.
Okay.
I mean, dielectric materials people are studying like for over a century, but for silicon nanosphere, silicon is like probably the most studied material in the world, you know. So, yeah.
Any other question from anyone? Okay. Then thank you,
Okay,
sir.
so thank you very much. Yeah, and please you can reach out to me to all the students. You know, if you think that you want to talk to me or need help or something, please don't hesitate. Okay.
Okay. Good, Joy.
Okay. Yeah.
Yeah, I'm here. Hello.
Now, vote of thanks.
Yeah, so we are at the end of the today's program actually, and I would like to request Dr. Kunal Sinha, Assistant Professor of Atosh College, to present a vote of thanks to our speakers. Thank you, Dr. Kunal.
Okay, thank you, Dr. Nandujal. Well, the honorable speakers, respected faculty members of various academic institutions, and invited guests, it's a privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of Electronic Science Society of India and the entire team, let me extend a very hearty vote of thanks to both the speakers for gracing their important works and sharing with us your findings and opinion today. A very big thank you to Dr. Saurabh Kumar Mukhopadhyay for his effort in the field of medical instruments engineering. The present state of research in the field of ECG is wonderfully shared to us in very easy and lucid language. I hope not only the faculty members but also the undergraduate students have also gotten wonderful exposure to the field of modern medical science instruments after studying in the topics in electronics. There are ample opportunities for working in this domain not only in India but abroad in research as well as in the industrial companies. I also must mention our deep sense of appreciation for Dr. Uttam Manna for his explanation on research in the field of nanoplasmonics. Dr. Manna has shown us the fascinating world in this area with his excellent presentation. The works on the dielectric material will motivate young students to do research more in this field, and he has also shared latest research topics in this area of nanodielectrics and the area where he is currently doing research, and we got a feeling of research in this topic. Once again, I want to state that we are all very grateful to all the speakers on the stage. We thank you for your being with us in this evening here in India and morning in your location. And it's been a great pleasure for staying with us and enjoying the entire program. Thank you very much.
Thank you. Yeah.
Bye. Yes, sir.
Over to you, Dujada.
Yeah, okay. Thank you all the participants, and we are hopeful that we will be back with another session of this sort of webinars probably next week or so. And I would like to thank everybody, our respected speakers, our participants, our teachers who are there in the webinar itself, and everybody who will watch this on our Facebook page later on and will know that, as Dr. Manna said, so nobody is exceptional except a few cases. So we are all common human beings, and if we have the zeal, if we have the determination in us, we can reach anywhere in this world, and I think beyond with electronic science. Thank you all for your participations. Good night.